Today the discussion, is the continuation of what we talked about yesterday, but we'll go a bit more in depth, but focusing on latent variable generative models. So the first two classes of models that we presented yesterday, first beginning with generative adversarial networks, and then going on to variational zone coders. Okay? So a quick reminder of the things that we discussed yesterday. So first, when you have a latent variable generative model, the density that you're defining can be written as a marginal integrating over latent variables. That's the first line here. Okay. So as we discussed yesterday, in the context of deep generative models, this integral is intractable. And so you need to devise ways of training your model anyway, trying to maximize this quantity. So that's the case for the VAE, where you define a lower bound on this quantity, then this lower bound is tractable, and that's what you maximize. In the case of GANs, you avoid the computation of any intractable integral using a network called a discriminator to replace this integral, and it's in a way a trainable loss. So that's what we discussed yesterday. So before we go into details on, let's say, refinements of each of these models, let's have some high-level discussion about what they do. So in some sense, these two families of models are symmetric to each other. They have very complementary strengths and weaknesses. And let's try to see this intuitively. So when you train a VAE, you're doing maximum likelihood training. What happens is you sample from P star being the true data distribution that you're trying to model. So in practice, it means you're taking a point from the training set, a real image. And once you have this image, you evaluate its score under the model, so the probability that the model gives to this image. So you evaluate the probability under P theta, okay? And you will reward the model if it gives a good score to the real image, and you will penalize it if it doesn't. So what you're doing is you're explicitly optimizing the coverage of training points under the model. Okay, you're pushing the model and rewarding the model when it covers points of the training set. What you aren't doing when you're training in a maximum likely manner is taking a sample from the model and evaluating its quality. Okay, you never do this in maximum likelihood training. In a way, it's done implicitly, of course, because we're training a density, so it normalizes, it has a total mass of 1. So if you put mass in bad regions of the space, so let's say on very unrealistic samples, you're taking away mass, so you have less mass to put on good training points, okay? So implicitly, pushing the model to put mass on real data points will also encourage the model not to put too much mass in bad regions of the space. But it's implicit, okay? So that's going to have, in practice, that's going to have implications. Now, when you train again, you're doing exactly the opposite. You're taking a sample from your model, and you're evaluating it by giving it a score. So ideally, you would measure the score of this sample under P star, but of course you can't do that, so you approximate this with a discriminator. But the idea is that you're evaluating samples, and you're never verifying that the model covers training points well. Okay, so it's symmetric to what you do with maximum likelihood. So you implicitly optimize the coverage of training points, and you explicitly optimize sample quality. Okay? So these procedures are quite symmetric in a sense. We can have a visualization of this in a case with very simple models. So we can take, let's say our model is a one-dimensional Gaussian, and our ground truth is also one-dimensional, but has two modes. Okay? The image on the left, the blue one, here, will correspond to what maximum likelihood does. So we'll begin by taking a sample from the data distribution, the gray line. It's going to be where the blue lines are. Okay, we sample from the gray distribution. And then we train our model to put mass on these points. Now, if the model is not flexible enough, in our case it's a one-dimensional Gaussian, so it has only one mode. It's never going to have two modes. So to cover these 2 points where the blue lines are well, it will have to go through regions of low density under the true data generating distribution. Okay? So to cover these 2 points here, it has to go through this region where there shouldn't be any mass because it's not flexible enough. Okay? That's the consequence of optimizing the model to cover training points. So in practice, you get overgeneralization. When you sample from your model, you're very likely to sample well from the mean, and you will arrive exactly in this region where you shouldn't have mass. So you will be very likely to produce bad samples. Okay, I hope that's clear. Now, if you look at what adversarial training does, on the other end, it's the exact opposite. So it's the curve on the right. In adversarial training, you're going to take samples from the model, so the brown curve, and these samples, let's say, are going to be where the red arrows are. Okay, and you will penalize the model for putting too much mass there. But again, since your model is a one-dimensional Gaussian, it lacks flexibility. It has only one mode, so to avoid putting mass outside of the left mode, you will have to drop the right mode entirely. That means you're going to miss almost half of the training support. Okay? And that's the consequence of doing adversarial training with a model that is less flexible than the ground truth. Okay? So I hope that convinces you visually that these 2 approaches are symmetric in a way and have complementary strengths and weaknesses. Maximum likelihood will tend to cover the support well, but generate bad samples because it overgeneralizes. And adversarial training will tend to generate good samples, but miss part of the support because it mode drops. Okay?
I have a question.
Yeah.
So here we have on the right hand side we have a bimodal distribution.
Yes.
So if we train a model, would it likely prefer the low variance mode or the high variance mode? Which form of mode parameter?
It should prefer the mode where there is the most mass. Okay? The mode where you're most likely to sample from under the ground truth distribution. Okay, in this case, okay, I'm not actually sure that it's the left one, I didn't check, but let's say if there is more mass in this mode, then this is the one you expect the model to focus on.
Okay.
Yeah. Well, actually, you're right, maybe there's more mass here, I didn't check.
So that's
what okay, yeah, it's possible that this is bigger, actually. Never thought of that. Okay. Yeah, okay, so this is just what I say written. Okay, so maximum likelihood might go through regions of low density, and adversarial training avoids low density regions. So, as I say, the consequence of this is that you can expect GANs to yield better looking images. That's the take-home message, I guess. And you can expect VAEs to better compress the training data. Here, what I mean by compress is, well, let's say you wanted to use your model to compress your data using encode your data using the distribution. Yeah. Okay, so now let's talk about some research direction that we're going to discuss today. So first, we're going to discuss better losses for GANs. So we said yesterday that training GANs is quite unstable, so hopefully there are ways of improving the losses to have better stability. And also, we'd like to encourage full support. So try to mitigate a bit this tendency to mode drop. And for GANs, we'll discuss how to avoid poor assumptions. Okay, to the elbow that we described yesterday, typically we make pretty strong assumptions about the distributions over latents and over images, so that it's tractable. And some of these assumptions might be costly and lead to overgeneralization. So we'll try to improve on that. Okay. So I'm going to start with a discussion about GANs. So first, let's verify, looking at the loss, what we said in the introduction. Why does the GAN tend to mode drop? Okay. I mean, we had an intuitive explanation, but let's verify how it happens with the equations. So first, recall. Well, the Kullback-Leibler divergence, you have the equation given here. It's equivalent to maximum likelihood training when it's written like this, because, okay, let's say you're training with this divergence. The term here is independent from your model Q, okay? So when you differentiate, the only thing that is left is this term, which is exactly, well, up to the sign, it's maximum likelihood training, okay? So this is what you do when you do maximum likelihood training. So a comment on this distance, if there is a 0 in the support of P, if there is one point that Q doesn't cover, then this distance, this divergence becomes infinite. Okay. With VAs, we have Gaussian densities, so there is never a 0 in the support, so that's not an issue. But that's not something to keep in mind. When you're using KL divergences, you cannot have a 0 in the support of the distribution that is to the left. Okay? If you have a 0, then you get an infinite divergence, you can't use that to train. Okay? So we should keep that in mind. Okay, now we said yesterday that the discriminator, if you assume that it's optimized perfectly, so it reaches optimality at every iteration, you can show that it approximates this loss here. So a comment on this loss, well, first it's made up of two KLs, but they're symmetric to each other. In this one, P is on the left, and in this one, Q is on the left. It means one samples from the model and one samples from the ground truth distribution. Okay? So that seems to contradict a bit what we said earlier about the GAN only evaluating samples, right? However, if you go back to the loss that you use, what you implement to train the GAN, it looks like this. So let's give it colors. So on the left, it's going to be the term that evaluates when you sample from the true data distribution, and on the right, when you evaluate samples. Okay, so that's the discriminator loss. As we said, it approximates this ideal loss, and the left term approximates the left term. Okay. So now a comment. If you look at the blue term in the first line here, you can see that it's independent from the model. Theta doesn't appear in this term. Okay. That means when we differentiate with respect to the weight of the generator, this term disappears. Okay. So you can't use this term to train the generator, which means that this term disappears as well. Okay. So only this term is left, and it is indeed an integral on Q. So we are training only by evaluating samples. Okay. So this was pretty clear from the intuition that we discussed in the beginning, but looking at the equations, you can confirm it. The discriminator definitely approximates the Jensen-Shannon, but you can only use half of it to train your generator. So if the generator is trained on the reverse Kuback-Leibler, reversed compared to the one we use in maximum likelihood training. Okay. So that's, the generator is trained on the red term. So let's keep that term. As I said, it's an integral on Q, and it's in a sense symmetric to what you do in maximum likelihood estimation. So the drawing that we showed is relevant again. You see, the red term will give you the curve on the left, and the blue term will give you the curve on the right. Okay. So we verified the intuition. So now let's go back to improving the way we train GANs. Why is GAN training difficult in practice? So the first thing that makes it difficult is that it's very, if you have a discriminator that is too strong in a GAN, it's very hard to train a generator because it leads to vanishing gradients, especially if you use the original loss, the one that we presented yesterday. So I'm going to make a drawing on the board for that. So let's say this line, okay, a discriminator, if you look at its last layer, it's a linear operation, so you can see it as separating the space in two. I mean, or even if you look at the inputs, in fact. So let's say this is our discriminator. And let's say that it's a very good discriminator in the sense that it discriminates real samples and fake samples with very good certainty. So that means there is a big distance between the reals and the fake. Okay. So there is a big distance there, and then we put a log which maps this to probabilities. Okay, so that's what a very strong discriminator would give us. Now let's say we train our generator and we improve our generator a little bit. So it will bring fake samples slightly closer to the boundary, okay? But when we differentiate, let's say here there was a big distance. Let's call it, well, not D, let's call it dist, okay? And we've made a small improvement, so we've improved by delta dist, okay? So now our loss function has a term that looks like dist minus delta dist after the improvement, and we put this in a logarithm, sort of, okay? So if this was very far from 0, so this is in the region where the log is flat, okay? So we make a very small increment here. Here it almost doesn't change anything, okay? So our gradients are going to be almost 0. So that's the high-level intuition of why if you have a discriminator that is too well-trained, it's going to be very hard to have a gradient that points to something useful, especially if you're using a log function here. It would make the problem of vanishing gradients even worse, because the log cares about the scales. Okay. So this is especially bad at the beginning of training, because when you start training, the generator is initialized randomly, so it produces very non-realistic looking images, which are very easy to discriminate. So at the start of training, you're always going to be in this situation. Okay? So you cannot start training, because at the start the discriminator is too good. If the discriminator is too good, you can't train, so you're not going anywhere. And that's what has complicated training of GANs at the beginning. Okay? So again, it happens it's especially bad at the beginning of training. So the main solution to this problem is to make sure that the capacity of the generator and the discriminator are well tuned. Okay? If you see that your discriminator is too strong, you try to reduce its capacity so that it doesn't do such a good job of discriminating, so that you hope you don't get vanishing gradients. Okay? That's the first solution. But of course, you can imagine that this requires time and human labor. So that's not well, it slows down progress, let's say. There is a trick that you can use to help the situation at the beginning of training. Instead of minimizing, you can replace the normal loss for the generator by this one. It has It has the same stable optima, so you're not changing the solution that you hope to get, but it will have stronger gradients at the beginning of training. Okay, so that's going to help a bit at the beginning, because now you're not in the region where the log is flat. Okay, but okay, these are not very important. It has the same stable points. The thing is, it's only going to help at the beginning of training. Then later on, if the discriminator becomes too good, the problem reappears. Okay. So it's a little trick that helps, but it doesn't solve vanishing gradients. So the question is, can we think of a better ideal loss for the GAN to approximate, one that doesn't suffer so much from this vanishing gradient issue? And that's the idea behind the Wasserstein GAN. Okay, so the Wasserstein GAN is inspired from Wasserstein distance, which is also called the earth mover distance. So let's speak a bit about this distance. First, let's consider that we have two variables, x and y, and a joint distribution between them, gamma. And, well, we can marginalize these joints with respect to x or with respect to y, and that will give us two distributions, okay? So you can think about the conditional on y, the density on y given x, as something that moves mass, that takes the variable x and transforms it into y. So for a given x, it won't be deterministic because it's a density, but it's going to tell you where you are likely to move your y. Okay. So it's a transformation in a way. So can we evaluate the cost of this transformation? We can write this integral here So we're going to be looking at the probability of taking x and y, and we're going to be looking at the distance between the two here. And when we integrate over all possible choices of x and y, this gives us a notion of how much it costs us to use this conditional to move the mass. Okay? Of course, it can also be written like this, sampling x and then moving into y. So, you have to think about this quantity here as the cost that is associated to our joint gamma. And the intuition is, how much work do I have to do to move each point under P to points under Y? Okay. So now, the Wasserstein distance is the cost that we'll have to pay to put the best possible joint, the best possible gamma. Okay, we're going to look at all the joints that we could take, and we'll select the one where we have the least distance to move each point from P to points of Q. That's the Wasserstein distance. So this distance has some nice properties. So to see this, let's take maybe the most simple example that one could think of. So our space is going to be two-dimensional. Here we have two dimensions. Okay. And we're going to take two distributions, P0 and P theta. One that has a support, well, both have a low dimensional support, both have only one dimension. So P theta only puts mass on the orange segment, P0 puts mass on the orange segment, and P theta puts mass on the blue segment. So now the question is, what's the Wasserstein distance that we pay if we choose these two distributions? So again, what's the cost that we will pay to move the blue line onto the orange line? Okay, so if theta is equal to 0, the Wasserstein distance will be 0, and the Jensen-Shannon will also be 0, and the KL will also be 0, okay? But if theta is different from 0, as we said earlier, if you have a 0 in the support of the density that is on the left, the KL becomes infinite, okay? I hope that's clear. So in this scenario, the KL divergence will be infinity for any value of theta that is not 0, okay? The Jensen-Shannon will not be infinite, it will be log of 2. So it's going to be a constant. All right? No matter where you put your theta, you could put it very far, it's always going to be the same value. So, of course, when you train, this constant, when you differentiate it, becomes 0, so you can't use that to train either. You won't be rewarded for bringing theta closer. Okay. On the other hand, if you look at the Wasserstein distance, it's going to be theta. And that's where that's why this distance is very pleasant. Even though we don't have any overlap in the supports, our distance will be proportional to the length here. Okay. So, in a sense, it feels like we're going to be able to work with densities that have non-overlapping supports. Okay. So, to put it into a one-liner, Wasserstein is based on the proximity of the supports, and the Jensen and the KL are based on the overlap of the supports. So you need overlap to be able to work with Jensen and KL. Okay? And you don't be able to work with Wasserstein. So in general, when we work with GAN, we expect to have 0 overlap. We have low-dimensional models, because we train a nonlinear mapping, but we don't add volume around it. So we expect to have non-overlapping supports with the ground truth. So yeah, why is that? Well, GAN, first of all, the GAN, in the image space, the dimensionality of the manifold that it learns is of the same dimension as the space in which we fit RZ. Typically, it's lower dimensional. Okay? So it sounds like, at least in theory, in this ideal regime where we've learned the Jensen-Shannon perfectly, it sounds like we shouldn't be able to train again. In practice, the discriminator is not trained to optimality and it still works. But there is something degenerate about using these ideal losses. Okay. So now, how can we work? Okay, it's nice. We have a Wasserstein distance that seems to behave the way we would like it to behave, but also this quantity here seems quite complicated to compute. It's a complex integral. We have to look over the entire families of marginals. It doesn't seem very doable. Luckily, there is a duality formulation of the Wasserstein distance, which is better to work with. So you can show, we're not going to do it, that this is equivalent to looking at, so we're going to look at functions that are k-Lipschitz. Okay, we're going to pick a constant k, and we're only going to consider functions that have Lipschitz norm bounded by k. Okay, and if we do that, we can show that maximizing this quantity within this family of functions that have Lipschitz norm smaller than k is equivalent to finding the best joint gamma. Okay. Yeah. So the notations here. This denotes the Lipschitz norm. So in practice, how do we do this? Because this set of functions with that are k-Lipschitz, well, it's reduced compared to any function, but it's still very big. So what we're going to say is we're going to consider that petit network is a universal approximator, so we can get close to any of these functions. And so what is left to do is to make sure that our network is k-Lipschitz. Okay, we'll say our network is k-Lipschitz, it's in this set, and because it's a universal approximator, we'll consider that it's able to approximate any k-Lipschitz function. Okay, so we have two things to do: choose a network architecture and make sure that it's k-Lipschitz. So how do we do this? Well, the first paper that proposed this clipped the weights of the discriminator. Okay, there is another. So we'll see this into a bit more detail later, but you can also use the penalty on the gradients. But let's say for now that we clip the weights. So at every layer, we clip the weights to enforce Lipschitz continuity. And since our nonlinearities are either contractive or, in the case of Radu, it's either 0 or the identity function, that's not going to have any impact on the Lipschitz constant. So if each layer of the network have a bounded Lipschitz norm, then the whole network will as well. It will be bounded by the product of these norms. Okay. So yeah, if you look at this loss, it looks very familiar. It looks very similar to the normal GAN loss, except here, instead of an unconstrained max, we have a constrained max, and also you can notice that the log disappeared. We don't have any log here. Okay.
Sorry. What is K?
K is the constant for that bounds the Lipschitz norm.
Yeah. How do you choose it?
It could be any value. Typically, people will take 1. Okay. Why can it be any value? Well, basically, if you have a network that is bounded by k, if you just rescale all the weights, you can have any other constant. So what matters is that the Lipschitz norm is bounded. It's not really the value that it takes. It'll just, if you take your space and spread it apart, you increase the function, but it will be the same problem. Okay. Of course, numerically it won't be the same problem, but in terms of ideas, yeah.
So the previous slide, 13. Yeah. So here, since theta is one-dimensional, we simply take the magnitude. What if it's multi-dimensional? Is it the L1 distance or L2, or how do we do it? Or does it make a difference or not?
So it's going to be hard to compute if you don't have a simple drawing. But I mean, for instance, if we just tilted these things, it would still be the distance between the two lines. You can just shift your base, and as soon as you start having lines that are non-linear, you're going to have to do some computations, because essentially you have to compute use the equation to compute the Wasserstein distance, so that's not easy. I cannot do it by simply looking at curves, let's say.
Okay.
Yeah. Okay. So Again, the two main differences compared to our previous GAN function, the analysis is very different, but in the end we arrive at a result that is very similar. That can be surprising a bit, at least it surprised me in the beginning. So let's keep in mind what differences this led us to. No log, as we said, we expect to help with vanishing gradients. So no log, and we constrain our function, our set of functions to be in k-Lipschitz. So we've added a regularization term. That's the two main differences that we obtain in the end. Okay. Yeah, here is another. Okay, I can't do it. Here's an illustration of what you expect. So the red curve would be what you expect to see with the typical GAN loss. So as you can see, you have a strong signal in between, but as soon as you go away from the middle, your gradients vanish. Here, you can't even see them. Whereas with the Wasserstein distance, you will have something that is much smoother. So you will have training signal, much better training signal, far from the boundary, at least in theory. Okay, in this case, we have two versions. So, yeah. So experimentally, using the Wasserstein GAN loss may lead to a more stable training. And also you may expect a better correlation between the loss of your discriminator and the quality of your images. So that's why they propose calling it a critic more than the discriminator. So this is what you would observe, you may observe with the standard GAN. As you can see, the quality of the images improves, and yet the blue curve, that's the loss of the standard vanilla GAN, keeps getting worse. So the discriminator is more and more certain of itself, and yet the quality of images improves. So it doesn't seem to correlate very well. In contrast, if you use the Wasserstein GAN loss, you may observe something that correlates better. Okay? The loss tends to decrease as the quality of images improves. So in practice, that doesn't always happen. Theory tells you that it should, that there is a big gap between the ideal setting and the practice. But still, it sometimes happens. Okay. I think I reversed my explanation. Okay, whatever. So, yeah, is this analysis relevant in practice? What we can say is that the analysis that we made about the Wasserstein versus the KL, overlapping support, non-overlapping support, is definitely true about the ideal losses. Okay, it's mathematically correct. So if you do it considering that your discriminator has perfectly approximated these two quantities, then it's totally relevant. In practice, we end up with something that is quite similar, as we've said before. The main difference is the disappearance of the log and the addition of this regularizer. But, I mean, these ideal losses, they're approximated by exactly the same networks, right? So the only difference is the training loss. We have the same discriminators plus a regularizer and no logging loss. We can also say that non-overlapping support, even though it's a problem in theory for the vanilla GAN, obviously in practice it doesn't break the discriminator. The discriminator just looks at pairs of images, it doesn't care if they have overlapping support. You can run your network. Okay? So this analysis is very interesting. It has led to an interesting regularizer and better losses, but you have to keep in mind that it's with respect to the ideal losses, and in practice it's not so different. Okay, so the conclusion of all this is that constraining the Lipschitz constant of a discriminator is a good idea. And removing the log helps with vanishing gradients. Okay, I should have maybe said that before, but as a reminder, what does K-Lipschitz mean? It means that you can bound, I mean, if you take the distance between your inputs, it will give you a bound the distance between your outputs. Okay? If you have linear function, one way of computing this, okay, here I chose one Lipschitz, I didn't put the k. If you have linear functions, you can just look for the largest eigenvalue of the function that will give you the constant. Okay. So, as I said originally, in the original paper, they did it with gradient clipping. The Lipschitz continuity is still widely used, but clipping is not the best way to do it. So there are two very popular ways to do this. The first one is spectral normalization. It's rather recent. So in this approach, the idea is that you're going to approximate the spectral norm using a numerical scheme that is called the power iteration method. Let's just believe that it approximates the spectral norm. And then we will divide each weight matrix by its spectral norm. So it will have a spectral norm of 1. That's trivial if you don't believe me. I mean, if you don't see this, just believe me. And so the spectral norm of the full network will be bounded by the product of the norms of each layers, and we say it's 1, so the full network will have a Lipschitz constant of 1. Yeah. Another approach, which is maybe less computationally expensive, is to penalize the gradients. So you can show that if you add this penalty here to your training loss, you should get something that has a Lipschitz norm close to 1. You won't be able to guarantee that it's exactly 1, but then you're not able to do that with spectral norm either because it's an approximation anyway. So yeah, these are the two popular methods of doing this. And yeah, definitely in practice, they've stabilized training of GANs a lot in the last years, and they're used by any paper that comes out, basically uses one of these two approaches. Okay, they're inescapable. So a lot of other losses, and like really a lot of other losses have been developed for GANs. We're only going to cover these because, well, I think they're maybe the ones that are the most widely adopted. And yeah, avoid using logs when training GANs. Alright, so that's it for the design of the Lipschitz Earth mover distance-inspired losses. So we're going to keep talking about GANs. And now we're going to speak about what happens if I want an inference network in an adversarial setup. So if we take the value again that we've been discussing so far, it lacks a mechanism to take a real image X and get a latent representation. You have a generator that takes latents and maps to images, but what you don't have is an encoder, as you would have in a VAE that takes a real image and gets a latent representation. So it could look something like this. That's one way of having an encoder in an adversarial setup. Okay? So what we'd like, so this is already in an adversarial setup, but just to show you here, we have an X. We map it through something that looks like an encoder to a latent representation. And we can also do the reverse here, take a latent representation and map it to an image. And then these things go into a discriminator here. So I will detail a bit more what all the blocks here are for. But for now, let's say, okay, we want to have an encoder and a decoder. Yeah. So now what's the difference in this setting? If you look here, you can see that the discriminator takes pairs of images. Okay? No, sorry, not pairs of images. It takes pairs of images and latents. Up to now, we were only feeding the discriminator images, either real or fake, and it had to say if it's real or fake. Now it will have to do the same, but with pairs. And essentially, it will have to say, am I looking at a pair where the image is real and the latent is encoded? Or am I looking at a pair where the latent is sampled and the image generated? Okay? So that's going to be the new task for the discriminator. And now we have an inference network. So you can, well, you can write the generator like this and the encoder like that. So we start by, in the generator case, we start by sampling the latent, and then we have a distribution on X that is a Dirac, because in the GAN setup, our generator is deterministic, okay? So that's why this distribution is a Dirac. And the same for the encoder. We sample a real image, and then we have a Dirac on the output of the encoder. That's if you want a probabilistic perspective. Okay. And so the discriminator looks at pairs of latent image. Okay. So if you're in the setup, you can, the training loss is going to be very similar to the GAN loss, well, except now, instead of images, we have pairs. Okay, but otherwise everything is the same. And again, you'll be able to show that the optimal discriminator approximates the Jensen divergence between the joint's latent image. At the optimum, again, it's a very ideal setting, but if you assume that everything can be trained to optimality, you should have a generator and an encoder that are inverse of each other. So that's the ideal thing that you would want from an inference network, that it's perfectly capable of inverting your generator. Of course, in practice, we never have this, but at least in the optimal setting, that's what we get. Okay, so let's look at examples of samples that you can. So BIGAN is a model that has this. It's not the only one, but it's one of the models that is constructed this way. Okay, trained on ImageNet 64 by 64. So here are samples that you can get from this model. Okay, and now let's compare. So this line here is if you take a real image, uncode it. I will code this. Take a real image X, uncode it, so you get a latent representation, and then decode it again. Okay? And if you look, you can see that the images tend to look like each other. For instance, if you compute the average color of these two images, you'll find the same thing, and they may share some global structure, but they're also still very different. You see, this is apart from the fact that there is grass and it's outdoor, there is not a lot of link between these two images. Okay? So that's not at all what you would get with the VAE. With the VAE, you encode, you decode almost the same thing as you encode. With the GAN, it's much looser. So it's not clear, to what extent it encodes a little bit of the image. That's clear, but how much it encodes is not clear at all. But still, we get an inference network, and we get realistic images. So we're going to be able to take a real image, map to samples, and get a real image back. Map to latents and get a real image back. So that's nice. And the bottom line is the same. It's just more examples. Okay. So one thing, why would you use this model? It's interesting, it's fun, but it's not easy to find applications for this, actually. So one thing that they propose is to compare it to self-supervised methods. So can we use this as a unsupervised pre-training tool? Okay, that's another thing we discussed yesterday. And they showed that on classification or detection or segmentation tasks, it can perform on par with the self-supervised method. So at least it seems like these latent representations are learning something useful. It's hard to quantify what they learn, but it's useful for unsupervised pre-training. So yeah, that's nice. Okay, so yeah. All right, let's discuss one more application that you can build using this concept. It's style. We can call this style transfer or domain adaptation. So the question is, could we learn mappings between two different image domains? Let's say I have a data set of horses and I have a data set of zebras. It's pretty similar. Can I use this construct to turn my horses into zebras and vice versa? Okay. And we want to do this without supervision. The only there is a little bit of supervision because we have to build two data sets, but that's it. So what that means is we won't have an image of a zebra that is almost the same as an image of a horse minus the stripes. This is not in the data set. This is the output of the network. Okay. Okay, you're missing a little bit of the image, but I think it won't be a problem. So let's say our two domains are 0 to the x, so we can say horses and y, let's say zebras. Well, we can use a discriminator to tell us if it's looking at a zebra or a horse. That's going to be, what we're going to use to encourage the model to produce zebras or horses, and we're going to condition on images of the other domain. Okay, I have a generator. I condition it on an image from one domain, I get an image from the other domain, and the discriminator tells me that's what's here, okay? And the discriminator tells me if it looks like an image from domain Y, all right? So again, I'm taking an image from domain X, using my generator to generate, hopefully, an image from domain Y, and I'm using the discriminator to tell me if it's indeed an image from domain Y. So if you do just this, maybe it's obvious to you that the generator could learn to completely ignore the image from domain X. It might even be easier. We've seen that the discriminator is perfectly able to generate, let's say, a horse from noise, so it could treat this as noise. It doesn't have to respect this structure here. We have the same structure, just the stripes are added. So how do you force the generator to respect the global structure of the image of the first domain? You use something which is quite natural, in fact, which is called cycle consistency. And the idea is, if I turn my horses into zebras, and if I haven't thrown away the global structure, then I can turn my zebras into horses again, and I expect to have the same horses as before. Okay, so I won't, and I can do this endlessly. So that's why it's called cycle consistency. On the other hand, if my generator kind of ignores the global structure of the first image, it's never going to recover it when I do a cycle. Okay. So, yeah, here's the full. I mean, you can do it in either way, and that's how you get. You need the two mappings to have the same consistency. So here are some funny examples of this exact model that we described. It works pretty well. And again, this is done, and that's why it's impressive. It's done without any supervision using aligned images. Here are examples with taking images and making them look as if they were taken in the winter. Sorry, in the summer. Well, oranges to apples. And a failure case. Probably there's not many images of him in the training data set. Okay, so a summary of everything we discussed so far. We discussed how to use, one motivation for using Lipschitz constraints in GANs, and that leads to improved classes of losses. If you build a GAN now, today, you would probably be well inspired to use Lipschitz constraints. Okay? We've also discussed how to build inference networks in the context of GAN. So actually, one thing that I didn't say is that we can expect this to help with the training support. That doesn't really offer guarantees, but the fact that we're looking at training images and encoding them into the latent space gives us hope that it should improve coverage of the training support by the GAN. No theoretical guarantees, but intuitively it should. Okay? And we can use this for a fun application of style transfer. And I guess you can build products with this. Okay.
Sorry, just a quick question.
Yep.
So in the previous examples, of course, there's nothing preventing the network from changing the other parts of the image apart from the post, and that's kind of evident also in some of the examples, like in the example.
Yeah.
The rocks there also these set of masses. But then what prevents them from doing that completely? In the sense that there could be a rock which is bigger than this. So why does the network not last?
You mean why don't we have stripes on the rock? Is that? Yeah, well, because the discriminator would, we're also giving the discriminator real images of zebras. And in a real image of a zebra, you don't have a rock with stripes. So if the generator does this, the discriminator should tell, well, this is a fake image, because rocks with zebras with stripes, don't exist. Of course, it doesn't work perfectly, as this example shows. The discriminator should not allow this. The thing is, there's probably not many pictures with a human on the horse, and so the discriminator never saw this failure case, and so it lets it pass. Yeah. Okay, that's it. We're done. Yep.
So how would we evaluate, except for just looking at
Evaluating GANs in general or style transfer?
Evaluating the generator outputs, like efficiency in general.
Yeah. So there is no straightforward, like very reliable way of doing it. That's a big problem with GANs. So initially I wanted to talk about it, but I decided not to. So I can give you the main intuition of, so people did build automatic quantitative evaluations of GANs, and I can give you the high-level intuition that is behind them. There are several metrics, but they all share this intuition. It's that you can take a classifier, let's say you've trained a classifier on real images, and the classifier is trained to tell you if it's looking at cars, boats, etc. So the intuition is that this classifier, because it has very good performance, should have an understanding of what a real image looks like. Okay? And so we are going to use one layer of a deep classifier network, very well trained, as features. Okay? So we are going to take samples, give them to a classifier that was trained on real images, and we're going to look at a deep layer and see if this deep layer behaves as it would behave with real images. And you can quantify this, okay? So let's say you have a big set of real images, you can feed them to your classifier, take a deep layer, that would again give you a big set, you know, each element corresponding to the original image. So you will get a big set of features, and you can model the distribution of this set of features. For instance, you could fit a Gaussian onto this distribution. So you get a representation of the set in feature space with a Gaussian model fitted on top of it. Now you can do the same with features, so with samples. Take a lot of samples, feed them to your classifier, take the same layer, and model the distribution. And now you can compare these two distributions, and if they behave the same, then you think that your samples look like real images. To see this, let's say we take, well, to see this in another way, let's say we take the last layer of the classifier. If it looks at a boat, it's going to assign a high probability to the class boat. So it's going to have very low entropy, because, you know, it's almost a direct low entropy. If you give it something that doesn't look real, it will not know what it is, so it will assign kind of random probabilities to, average probabilities to all classes. So it will have high entropy. So another way of seeing this intuitively is that you expect that when you give good sample to a classifier, it has low entropy, and when you give bad sample, it has high entropy. Okay? Two ways of motivating this. But the main idea is, let's use a classifier, which is supposed to know what a good image looks like, to evaluate how much our distributions look like each other.
So this is good only for quantitative evaluation.
Yes.
What would qualitative? So you do like SSIM sort of metrics, or
you could. So intuitively, that's another metric that you could use. It doesn't correlate as well as using a classifier, because it's too handcrafted. It works for simpler distributions, but for images not so well. If you really want a qualitative evaluation that is rigorous, you have to use humans. So you will take maybe 30 people, show them side by side real and fake samples, ask them to point to the fake one, record their performance, and you will say that the better model is the model that confuses humans most often. Of course, this is expensive, so you might use it at the end of your research to evaluate your best model, but you're never going to use this for your research to choose between 100 models. Okay? Yeah, well, maybe I should have spoken about GAN evaluation, but yeah. Okay, I think we can take a 10 minutes break. We're done talking about GANs. We'll move to VAEs afterwards, but in the meantime, 10 minutes break. So see you in 10 minutes. Thank you. Okay, so forget about GANs, get them out of your mind, and we're going to go back to speaking about VAEs now. So, quick reminder of what we discussed yesterday and what you saw with Pierre Alexander as well. So, VAEs, optimize the evidence lower bound, which is written here, and what we're trying to maximize is the quantity here. I'm missing a theta, by the way. Okay. So let's make comments on this bound. For tractability, the typical assumption, we discussed it yesterday, is to assume that the posterior here is Gaussian. That's useful for tractability, and it's even diagonal Gaussian. Okay, that lets us compute the determinant in an efficient manner, and we can have an analytical form for the other equation. Okay, so we make this assumption that the posterior is Gaussian. However, it's very clear that the true posterior, so this one here that we're trying to approximate, it's never going to be Gaussian. I mean, the variables are never going to be independent in this posterior. We can't compute it, but for sure it's not. Okay? So that means we're making an unrealistic assumption, and so our bound here is going to be looser than it would be if we didn't have this assumption. That's clear. Another thing is that it will encourage the true posterior to match this assumption, because I mean we're training this thing. Oops. This thing here is trained, even though it's not trained in this direction. It's trained in the direction z to x. But still, gradient descent will push this to match the assumption. So we're also, in a way, biasing the behavior of our decoder towards something because we had to make this assumption for tractability. So we're going to have a bound that is less tight, and we might also hinder the performance of our generator. Okay? So how can we improve on this? So the first thing that we're going to discuss is, for a given posterior, could be Gaussian, how can we make the bound tighter? So you discussed this with Pierre Alexander yesterday, so I'll be very brief. A second direction of improvement is to enlarge the family of posteriors, okay? And there is two ways of doing this that we'll discuss. The first one is using a hierarchy of latents. And the second one is how to use flow models to reshape these Gaussians. So keep Gaussians, but then use flow models to reshape them. So that's what we're going to detail. Okay. So, first thing, can we construct a more accurate bound? Okay. So you've seen this yesterday, so it'll be quite fast. So we can define importance weight, as Pierre Alexander discussed yesterday. Here, that's going to be what we call importance weights. And we can rewrite the evidence lower bound like this. So we've approximated the integral on z with a finite number of samples. Okay. Apart from this, this is the elbow. Because the log is concave, you can use Jensen-Shannon. What am I saying? Okay, I forgot the name. Inequality. The log of the expectation is bigger than the expectation of the log. Okay. Jensen, yeah, thank you. Oh yeah, Jensen-Shannon, that's right. Thanks. So Jensen inequality. So this is trivial. And, well, you can rewrite it as an expectation, of course. These are IID samples. These here are IID samples, so we can collapse it into this. Okay. And this is equal to the quantity that we're trying to maximize. So, okay, there is a trick here, is that I replace the finite sum by the expectation. So, some comments on this. The lower bound, the standard deviated lower bound will be recovered if you choose k equal to 1. Okay? This, if you do this, this becomes an equality, and you're back to where you started from with only one term. So the standard deviated bound. Okay? Now you can also show that as you increase the number of samples, the bound improves. Alright? And you can also show that if you assume the weights to be bounded, then you will converge to the right quantity as you increase the number of samples. Okay? So that's what we wanted to do. We can tighten the bound, and so there is a trade-off here. We spend more computation because we do more sampling steps, but our bound becomes tighter. Okay? We get a better bound. So there's two things we can do with this. For instance, we could use it at train time. Okay, so at train time, we'll use the reparametrization trick to take samples, but we'll take more than one sample and use this bound for training instead of the normal bound. Everything is still differentiable, it works fine. Okay. In that case, we'll probably take a value of k that is not too big still, because otherwise training is going to be too slow. Maybe k equal to 10. Another thing we can do is, if we've already trained a VAE with the normal bound, we can still, at evaluation time, tighten the bound. So we will not benefit from doing so at train time. It will not give us more flexible true posteriors, for instance, but it will still give us a better bound, so we'll be able to report a slightly better value. Okay? And in that case, we can afford to take a k that is very big, because we're going to do this computation only once. Okay? So we can comment on what the gradients look like if we use this bound instead of the normal VAE bound. Spare you the details, but okay, it's going to look something like this, where this is the normal term, but we see that we reweighted the terms in this sum by the importance weights. The importance weights, as you recall, are computed using the true posterior. So intuitively, what this is saying is we allow the model to sample in bad regions of the space more, because if it does, the true posterior will have a low value, so our weights will have a low value, and so we won't penalize the model so much. Okay? So it's allowed to make more mistakes. It can sample in a bad region, because then in the loss, we will tone down the contribution of this term and put more weights on the good samples. So that means we're relaxing a bit the constraints of our true posterior, and it might learn to model more complex distributions. Okay? So here, this is a simple drawing showing the case where we can compute the true posterior, but this relaxation might allow the true posterior to be multimodal, for instance. So on the right, we've been using this importance-weighted VAE procedure. Okay. So that's one way to make the true posterior and the bound tighter. True posterior more complex and the bound tighter. Okay. Yeah, you've seen this yesterday, I think so. That's all I'm going to say about it. Let's switch to another approach, which is, well, so far, we've been discussing encoders that look like this. So, go from X, we have a deterministic network that reduces the spatial dimensionality into a latent Z, and then we decode. But this is the only, in this network, so this is deterministic, and this is the only place where we have latent variables and that are modeled randomly. Okay. So one thing that you could ask is, why can't I extract latents at different steps in this process? You know, maybe I'm looking at my image, I encode it a little bit, and as I reduce the spatial dimensionality, maybe I can extract a latent Z that controls patterns or high-frequency signal. You see? Low-level detail. I could encode it here and call it Z1. And then maybe a bit later, I could encode something that controls the edges and call it Z2. And as I get closer, I will have latent variables that control the global structure of the image. Okay. And finally, I will have this one. So now I have a hierarchy of latent variables. That could be a very reasonable idea. Of course, then I will start from this latent, start generating an image, and then I can feed back this information progressively. Okay? That would be a reasonable idea. So here I decide that I'm going to generate a car, and here, well, I had extracted the information, this car is red, so I'm saying again, well, the car is red. Okay? So this is reasonable, you have hierarchical latents, but if you do it like this, there is a problem. It's that you're going to sample the latents when you generate, at sample time, when you start from here, you're going to be sampling the latents in the opposite order in which you extracted them. Okay? Here you started by extracting low-level details. So let's say what are the shape, what's the width of the wheels of my car, and at the end you extract the fact that it's a car. But at generation time, in fact, you want to do the opposite, right? You don't know that it's a car because you haven't looked at X yet. So you would first want to decide that you're generating a car before deciding the shape of the wheels. So you really want latents to be sampled in this order, starting from this one and going there. So that's why doing it like this is problematic. In fact, so the answer is already on the board. You need to do something that looks like this. So going up here would be the encoding, so this left triangle in my drawing. And while you do this, everything is deterministic. So at different layers, that be the H's, at different H, you will extract some information on Z, but it's going to be deterministic. So you set aside some information. You go all the way up, get your, let's say, highest level of abstraction Z, sample, well, so now you can sample, and now you go down and reconstruct. And as you reconstruct, you get the deterministic information that you had extracted before, combine it with what you know now, and sample again. This way, this is something you can do both when you encode and decode, and when you sample. And in both cases, the latents will be sampled in the same order. Okay? If this was a bit confusing, the take-home message is if you want to have a hierarchy of samples, yes?
Those sets in the hierarchy, are they still Gaussian?
Yes. Each, if you look at one, yeah. Typically, well, I mean, of course, no one forces you to do this, but the typical thing would be that Zi will be Gaussian, but knowing the ones that came before, okay? So, this is Gaussian, but when you integrate, I will show this later, that's a good question, it's in a later slide, so when you integrate, it's no longer going to be Gaussian. But yes, conditioned is Gaussian. Alright, so take-home message, if you want to have a hierarchy of samples, you need to make sure that they're sampled in the same order when you encode and when you decode. And it looks a bit like a ladder, so this construction is called ladder network. If you want to build a VAE that works with natural images, you have to do this. There are no VAEs, like the vanilla VAEs that we presented yesterday. When you apply them to ImageNet, it's always going to be very blurry if you don't do this. Okay? So all modern VAE architectures applied to natural images have this ladder construction with hierarchical samples. So, some comments. So you can see that if you build it like this, you have an autoregressive modeling of, let's say, your Z is the concatenation of all these little Z's that we sampled hierarchically. So we have an autoregressive distribution in the sense that we'll model the joint PZ1, PZ2 as PZ1 times PZ2 knowing PZ1. Okay. So as I said, same order when encoding or when sampling. And how does the VAE lower bound look now? Well, it's still tractable to compute. So this is still the same term. But now we have a sum of KL divergence. Of course, we need to, that's in the drawing. At every step, we needed to look at how much information we're injecting and pay the price, just as yesterday. So this is still tractable. Okay. So that's your question. The posterior on the full vector of concatenated latents is no longer Gaussian, even though we're using a Gaussian at each step. Well, for instance, if you look at Z2, Z2 knowing X, you can write it as the integral over Z1 of Z1 knowing X times Z2 knowing X and Z1. So this distribution here is a Gaussian, but when you do this integral, it's no longer Gaussian. So as you stack this hierarchy, the densities that you can model become more and more complex. With one step, it's already quite complex in here. Okay. Yeah, so that's it for improving the lower bound with hierarchical latent construction. Another thing that you can do, forget about hierarchical things, is use a Gaussian, but then reshape this Gaussian in a tractable manner. So with like a high-level picture of this would look like this. This is our normal encoder, this is our normal decoder, and this block here is where we would normally sample. But now instead of just sampling, we start by sampling, and then we reshape progressively this density many times into something that is more complex than a Gaussian. That's the high-level intuition. Of course, when we know how to do this, we can combine it with the idea of hierarchical latence, but they are two separate things that are easy to combine. So how do we do this? Well, it's the same idea as we used yesterday for the real MVP. So it was the invertible transformation where you don't need to compute the integral. So why is this idea coming back again? Well, because it's the construction that lets you reshape densities in a tractable manner. That's the thing to do when you want to still be able to compute the likelihood. Of course, it's also a big constraint, that these models should be invertible. So what is it going to look like now? Well, we're going to sample Z0, and normally we would have stopped there. But now we will apply a stream of invertible functions, f1 to fk. And if they're flexible, we will reshape our density on Z0 to something much richer on Zk. Okay? And as we saw yesterday, we can use the change of variable formula to compute the density, starting from the Gaussian, arriving in the other space, that's the change of variable formula that we saw yesterday, applied k times. Okay.
I have a question.
Yeah.
How is it different from doing this transformation as part of decoder?
So the goal of the encoder, you could do this, but flexibility of the decoder is not an issue here. The decoder is already quite rich and quite flexible. What we really care about is making our bound tighter by improving our approximation. So what we really want to do is make the encoder more flexible so that it can better match the decoder. Of course, you could add invertible transformation in your decoder. Why not? But tractability of X knowing Z is already not an issue. So if you want to add flexibility, just add layers. They don't have to be invertible. You're not lacking any tractability there. You don't have to pay an extra cost of using invertible transformations. Is that clear?
Yeah.
So what are examples of, so we saw one example, the real MVP, yesterday. There are other things that you could do. So the first thing that people tried were using planar and radial flows. So you could write them like this. They're pretty simple transformations. Here you see that you have a scalar product, so it will map Z to a scalar. So it's a bottleneck with one feature, if you want, one neuron. And you use this to reshape your Z. So these two transformations are simple and tractable, but they're not very expressive. This bottleneck of one feature, you can feel that it's going to hurt flexibility a bit. So this is what it could look like. Oh, okay, no. This is what it would look like in 2D. You see that depending on the number of K, you can reshape your Gaussian density more or less. So the blue line is starting from a Gaussian. Red line is starting from a uniform. And then as you add more transformation, you get your distributions that are more and more complex. Left is planar, right is radial. Okay. Okay, but of course these examples are in 2D. So the bottleneck here is not really a concern. Going from 2D to 1D is not a huge loss, but going from 1,000 to 1, that might be more problematic. So can we do something else? Yes, we can use autoregressive transformation. So that's the idea behind a very well-known model, but it's called inverse autoregressive flow. So we don't have to look at this complicated drawing too much, I guess. The main idea is, so this is the normal VAE construction. Here we're expecting, okay, so this is a normal encoder, so it gives us the parameters of the density on the Z. That's what we've seen so far. Here we're using the reparametrization trick, okay, that we discussed yesterday, to sample our z from our Gaussian in a manner that we can differentiate through without using reinforce. Okay. So now we have our first latent, and now we're going to reshape it several times. So each IAF step is one step of reshaping. And this IAF step is also going to be informed by some deterministic information that we extracted at encoding. We're allowed to do this, and it improves results. Believe me. Okay, so now what is this IAF step? Well, it's quite a smart transformation in the sense that it allows us to leverage autoregressive models, XLCNNs, we also discussed yesterday. So it's kind of a mix of every model that exists. There is the notion of flow, autoregressive models, and autoencoders. So how do we want to do this? We're going to take Z and apply, as with the real MVP, a scale and location transformation. And how do we get these parameters here? We use an autoregressive network. Why? Because as we said yesterday, what matters is, so trivially, this is going to be invertible, just as yesterday, we have a triangle. And we also want the Jacobians to be easy to compute. And that's the case when we have triangular Jacobians. Okay? And an autoregressive model is a triangle, okay? In the sense that you modify this point by looking at this point only, then you modify this point by looking at the points that were above, etc. Okay? So when you compute your Jacobians, they will be triangular. Okay, I showed it. This drawing is not great, but I think it's quite clear, so maybe there's no need to elaborate more. It's clear for everyone that using an autoregressive model will need triangular Jacobians? Yeah? Okay. So, we take our Z, we apply an autoregressive model to it. This gives us mu and sigma parameters here. And when we compute the Jacobian of this transformation, it's triangular, so the log determinant of the Jacobian is practicable to compute. That's all the ingredients that we need. So that's what's inside this IAF step. Apply, take your Z, apply an autoregressive network that gives you scale and location parameters, modify your X, and get a new Z. And thanks to the autoregressiveness, everything is practicable. Okay. So that's it for how to, that's I guess today is the best flow transformation used in the context of VAEs. Yeah. The I? In red, here? That would be so T is the number of steps that we do. So it could be number of IAF steps, it could be 1 or anything. In practice, it tends to be 1. That's how many times we reshape our density. And this number is the features in Z that we're allowed to look at. So when we're reshaping, that's the autoregressive thing. When we're reshaping feature number I plus 1, we're allowed to look at all the features that came before, so 1 to I. Yeah. Yeah, so that's how basically that's how a pixel CNN works. It takes a vector and it gives you an output where at each location you have something that depends on only the features that came before. All right? Yeah, I went a bit fast on this yesterday, so now it's not very clear. That's how it works. Okay, so these are the ingredients that we have to improve our elbow, or at least what we discussed yesterday. Importance weighted autoencoders to make the bound tighter for the given posterior, hierarchical top-down sampling, and flow transformation to reshape each latent in the hierarchy. In practice, state-of-the-art models combine these two things. Usually they don't use importance weighted at train time, but they will use it at evaluation time to improve a bit the numbers. Because, well, as you calculate the bound, you get slightly better values. Okay. So that's it about improving the posterior. Now we are going to discuss how to improve the decoder. Okay. It's going to be quite short. So one thing that is bad about, so far we've been using VAs with Gaussian densities as outputs, and the density, the Gaussian is diagonal. So in one sense that's bad because you're making a conditional independence assumption on X, okay? So if we say that X, given the latent, behaves like a Gaussian with mean mu of Z and variance sigma identity, it means that given the latent, we get a deterministic mapping, and as we sample, we're going to sample each variable independently around this mu, okay? And that's very good for tractability. It lets us compute the block determinants easily. But it's a weird assumption, because when you have an image, neighboring pixels are definitely very correlated. So of course, this mu of Z produces some correlations between your pixels, but when you're sampling, what you're essentially doing is you're taking this average image and you're adding salt and pepper noise on the image. Each pixel, you make it a bit darker or a bit lighter, and it's done independently for each pixel. So it's this weird idea that it's okay to add salt and pepper noise to the average image of the distribution. So I hope you feel that this is, well, not how natural images are created, and it's a weird model. Another way of seeing this is that when you take the negative log likelihood of your model, as we discussed before, it's equivalent to L2 regression. Okay, it's a diagonal Gaussian. And L2 regression is definitely, in some sense, a bad measure of similarity between images. For instance, if you take an image and slide it by a few pixels, the L2 distance is going to explode. Okay? And yet, a human will tell you that it's almost the same image. So, in some ways, this conditional independence assumption on X given Z that we make is good for tractability, but it's a bad model. Okay? And it means that you cannot learn any structure with the variance of your density. Anything that is not modeled by the mean, mu of Z, will be modeled as independent noise, so very poorly. So in practice it means everything goes inside the mu. Okay? And this leads to blurry images, because if your mu is not flexible enough, you model the uncertainty in a bad way. And blurry images, in turn, lead to overgeneralization, so bad samples. I mean, it's not that they lead to, it's a symptom of overgeneralization, sorry. So, yeah, I hope I've convinced you. It's maybe a bit subtle, but that this conditional independence assumption is a bad modeling assumption. And the question is, can we improve on that? So, what we're going to do is try to use autoregressive models to induce variance at sample time. Okay? So we're going to rely on the variational, the VAE, to deal with the global dependencies in the image. Okay? Take a Z, get the mu, and that's going to control what our image looks like in terms of global structure. And the VAEs do this very well. Okay? But these models, if we just do this, the pixels are conditionally independent, and we don't want that. So to improve the distribution, we're going to use an autoregressive model. So we condition our pixel CNN on something that comes out of the VAE that controls global dependency. And for the low-level detail, or high-frequency signal, we rely on a pixel CNN. Okay? So it would look like this. This is the decoder of the VAE. And at the end, we condition on the output of this model, and we use a pixel CNN to model the density of images. Another drawing, so this is just a VAE. You can see our encoder, we sample Z, we decode it. And now we add some pixel CNN layers. So we have these layers with the masking that we discussed yesterday. And now this will give us a richer, okay, this is how it looks if you write this. So here is the posterior that we're used to, and this is the step. Sorry. So we're sampling with respect to latent variables. Then this is the normal VA decoder, and then we condition a pixel CNN on it. So we're going to be able to model pixel Y, given the VAE representation and the pixels that came before. That means if I'm looking at an image, okay, let's say my image has 9 pixels. With the VAE, I would have sampled all these pixels at once. With this construction, I will get a global representation, f of z, that I will use to sample the first pixel, okay? Then, to sample the second pixel, I will look at what I got for the first pixel, and again at f of z. So this means now I'm not adding salt and pepper noise anymore, okay? Each pixel is sampled looking at what was done before, so it can adapt. That means if I decide to put the edge of an object here, this pixel here will be aware the previous pixel was an edge, so that the object is finished, and it will, let's say this was the edge of the car, so now this will be drawing the streets, for instance. And that's going to improve a lot on how blurry my images are. Okay? Okay, this is very intuitive, but that's the key idea. So let's look at how this works in practice. So how we implement this is simple. We concatenate a VAE with a pixel CNN. Okay? Yeah?
Strange question. You always get or generate the pixels by lines.
Yes.
Have you tried anything like Hilbert? Sorry, curve. Yes, Hilbert curves or space filling curves. So it's completely different. They
okay.
on
Yeah.
the space
Ordering.
and then they can.
So it's true that this ordering is very naive. It's easy to implement. That's one good property about it. So there's been recent papers that experiment with smarter orderings than this. Typically, it's based on the idea of having a hierarchy. So they will start by generating the image at a low resolution, by generating a subsampled version of the image, and then condition on this, move to it looks a bit like what we presented yesterday, but without the notion of grouping, and I mean, it's still fully autoregressive. So yeah, definitely you can improve the ordering of the pixels. There's been some very successful papers recently that are based on this idea. Okay. But the vanilla example would be keep the scanline ordering, which is probably not ideal, but easy to implement. Okay, so if we do this, let's say we have a VAE that has hierarchical latents at 2 levels, okay, what we discussed before just twice. And then, of course, we also sample from the pixel CNN. So there are 3 steps where we sample. First, Z1, then Z2 given Z1, and then finally, all the pixels given F of Z1, Z2. Okay? So, this is a generated image where we sampled from the VAE, kept this representation fixed, but then sampled several times the pixel CNN part. You can see that it looks very similar because, well, if you look closely, there are some differences. For instance, the lower here is very dark. Okay, this wall here is different here and here. So the pixel CNN does have some stochasticity in the amount of detail that it adds, but not a lot of stochasticity. This is another example, so same here, very minor difference, but you need to look closely. I can circle one maybe. Here, okay, this image looks pretty bad actually, I don't know what that is, but it looks like there's a dog, well, yeah. Okay, now if you resample, okay, another one. Now this is what happens if you resample also at the VAE level. And now you can see that the global structure of the images changes much more. Okay? As we discussed, the VAE is very good at controlling the long-range dependencies. So if you resample from the VAE, it's going to have an impact on what the image contains much more. And then the VAE will add the detail. So you will end up with images that are much more different. They're still quite similar. Why? Because we didn't resample at scale 1 by 1. So that's the moment where the most global dependencies are modeled. So if we don't resample this, we will still get roughly the same image. Okay? Okay. Well, that's it. That's what I wanted to present today.